Hello everyone and welcome to Mechanics and Dynamics lectures. In this lecture, we solve a problem that illustrates the practical application of Newton's second law. In this lecture, we solve a relatively simple problem, and in the subsequent lectures, we will solve more complex problems. Consequently, if you're interested in this topic, please subscribe and press like. Also, please feel free to ask questions and give your feedback. You can do that by leaving a comment in the comment section below this video. Here is the problem formulation. The box with the mass of m is pulled by the force F. Due to the action of the force, the box slides on the horizontal surface. Initially, the box is at rest. The coefficient of kinetic friction between the box and the horizontal surface is mu. Determine A. Acceleration of the box. B. Velocity of the box after t is equal capital T seconds. And C. What is the minimum value of the force F that will lift the box? To solve this problem, we need to perform several steps. In the first step, we need to construct a free body diagram of the problem and we need to introduce the coordinate system. Let's construct the free body diagram. Here's our box. Let us first add the external force F. Here it is. Then, if we remove the horizontal surface, instead of that surface, we need to add reaction forces. So what are the reaction forces? We have normal reaction force, that's the vertical component of the reaction force resultant, here's N. And we also have a friction force. However, we need to find the direction of the friction force. Due to this external force F, or more precisely due to its horizontal component, that is, due to this component, the box will move in this direction. This means that the friction force will act in the opposite direction of the direction of the movement. That is, the friction force will act like this. This is F mu. The subscript mu comes from the fact that we have the kinetic friction over here. That is, we have the coefficient of kinetic friction that's denoted by mu. In addition, we have the mg force. That is, we have the weight of our box. Here's mg. And finally, over here, we'll write the angle. The angle is 45 degrees. That's our free body diagram. Next, we need to introduce the coordinate system. My x-axis will be in the direction of movement. Here's x. And the y-axis is perpendicular to the x-axis. Here's the coordinate system. This was the step number 1. In step number 2, we need to construct the so-called kinetic diagram. To construct the kinetic diagram, we will draw our box once more. Here it is. And we need to draw the acceleration vector. Obviously, over here, we know precisely the direction of the acceleration vector. Namely, due to this horizontal component of the force, the box will move in the right direction. And consequently, ma is the so-called inertial term, where a is the acceleration vector. Perfect. To make this video tutorial as clear as possible, over here I repeated the free body diagram and the kinetic diagram. The next step is to determine the equations of motion. To construct these equations, we need to apply Newton's second law. Let us write Newton's second law in the vector format. Mass times the acceleration vector is equal to the sum of all the forces acting on this system, that is, acting on this particle. We have normal force N plus F mu plus mg and plus F. You should note over here that this equation is actually a vector equation. Later on, we will introduce projections of this equation. Here, it's very important to observe the following. Obviously, the acceleration vector only has an x component. That is, we can write the acceleration vector as ax times the unit vector I of the x-axis. So this is the unit vector I, and this is the unit vector j. Next, let us project this equation onto the x-axis. To do that, we will simply multiply this equation, and I will denote it as a star, by the unit vector of the x-axis. That is, we will scalarly multiply this equation by I. And as the result, we obtain the following. max is equal to ma, and let's see what are the x projections of this equation. Obviously, n doesn't have an x projection, as well as mg. However, f mu has the projection, and we need to write minus f mu. Also, the force F has the x projection, and that projection is plus F cosinus 45 degrees. We know that the force F mu is actually not completely independent from the normal force. That is, there is a relation between F mu and n, and that relation is mu times n. By using this equation, we can write max is equal to ma, and that's equal to minus mu times n plus f. What is the cosinus of 45 degrees? The cosinus of 45 degrees is square root of 2 divided by 2. And this is our first equation. We need to determine the acceleration a. However, here's the problem. We don't know the normal force n, and consequently we need an additional equation. That additional equation is obtained by projecting this equation onto the y-axis. Consequently, over here I will write star scalarly multiplied by j, where j is the unit vector of the y-axis. Let's see the projections. Obviously, the acceleration doesn't have the projection onto the y-axis, so we can write 0 for this part over here. N projection is simply n. F mu doesn't have the projection onto the y-axis, and we also have minus mg. In addition, we also have the projection of the force F onto the y-axis. So we need to write plus F multiplying sinus of 45 degrees. From this equation, we obtain that 0 is equal to n minus mg plus f square root of 2 over 2, since sinus of 45 degrees is square root of 2 over 2, and from this equation, we can actually express n. N is equal to mg minus f square root of 2 over 2. Perfect. Here are the two equations that we need to combine once more. We need to substitute n from this equation in this equation. Let's do that. ma is equal to minus mu multiplying mg minus f square root of 2 divided by 2 plus f square root of 2 divided by 2. And let's rearrange this equation. ma is obviously equal to, let's see what happens over here. I have f square root of 2 over 2, this term over here, and over here I have minus mu multiplying minus f square root of 2 over 2, and that's equal to plus mu f square root of 2 over 2. And I can group that term with this term, and as the result I obtain this term over here. I obtain 1 plus, let's see what do we have over here. We only have mu over here. And I have minus mu mg. Perfect. Now, what I can do over here? I can obviously divide this equation by m, and finally I can find the expression for a. So a is equal to f square root of 2 multiplying 1 plus mu divided by 2m. And over here I have simply mu times g. And that's our acceleration. Next, we need to solve the problem B. We need to compute the velocity at the time instant t is equal to capital T, where capital T is some fixed and given time instant, for example 5 or 10 seconds. To solve this problem, we need to express the acceleration as the first derivative of velocity. From this equation, we will obtain that dv is actually a dt, or velocity is an integral of a dt plus some constant c0. This constant should be determined from the initial condition. Okay, acceleration is given by this equation, and we will not substitute this equation immediately over here. One thing should be observed over here. Acceleration is constant, and consequently velocity is then given as a goes out of the integral, and integral dt is simply t plus c0. Let's determine c0. In the problem formulation, it's written that initially the system starts from rest. That is, the initial velocity is actually 0. And by substituting this initial condition in this equation, for time is equal to 0, we obtain that c0 is actually 0. And our final velocity is equal to a times t. And the velocity at the capital T is actually at. And finally, we can substitute the acceleration from this equation, and we obtain as the result f square root of 2, 1 plus mu divided by 2m minus mu times g. And everything should be multiplied by capital T. And that's the solution of the problem B. Next, we need to solve the problem C. That is, we need to compute the minimum value of the force F that will lift this box. Let's analyze this case. What's happening? F is acting in this direction. F has two components, horizontal, and it has a vertical component. This vertical component is actually the component computed over here. This equation originates from the projection of the equation of motion onto the y-axis. So let's write it over here. N is equal to mg minus f square root of 2 over 2. And this value again is the vertical component. Let's say that we can vary f. That is, we can increase f. If we start from 0, nothing will happen. If we keep on increasing f, at certain point, this box will start going upwards. So what is the critical value of f for which this box will start to go in the vertical direction? Let's see. What is the condition? If basically this term is always larger than 0, there is the reaction force. This means that mg is larger than f square root of 2 over 2. That is, mg is larger than the vertical component of the force F. However, what's the critical case? The critical case is n is equal to 0. At that moment, that is when we keep on increasing F such that n becomes 0, we will start lifting this object. So let's find the value of F. We simply substitute this expression in this equation and we obtain 0 is equal to mg minus f square root of 2 over 2, and we obtain that f is actually equal to mg 2 times mg divided by square root of 2. Let's verify that this is the case. Yes, this is the correct answer. So for f larger than or equal to 2mg over square root of 2, we will be able to lift this box in the vertical direction. Okay, that would be all for today. I hope that you like this video. If you like the videos I creating, please press the like and subscribe buttons. Thanks a lot and have a nice day.